Yeah, we did it. We're live again. Woo! Excellent. Woo! I don't know. Good morning to all. It is wonderful to see my face again at 7:25 in the morning on a Wednesday. It is cold and blustery, which I had to go out into the cold, but you got to stay home. You're probably in a blanket right now, which makes me very jealous because I would like to be in a blanket right now. I could be in a blanket right now, but it would look unprofessional because I need to look my best on any live stream that I do. But here we are. Oh, goodness. So anyway, just a small update for you guys that are in the chat right now. I'm still in the middle of grading the assessments that you turned into me earlier this week. There was an assessment that you had to do wrapping up the normal distribution. I'm still in the middle of grading those, and I should get those inputted probably within the next day or so. Things have been running a little bit weird left and right, just because we're trying to catch up on things and we have meetings, and I'd have it like after school on Monday. I had to go straight into like a 45-minute meeting on the computer. It's like, when am I going to find time to grade this stuff between teaching, blah 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 blah. Anyway, I'm rambling. Good morning. Somehow I think the number of people in the chat went from like 2 to 5 to 8 to 6 to 3 to 2 again. It's so weird. I don't get that. But anyway, we're going to start. Now, I would like to pick up where we left off on Monday. On Monday, I gave you a quizzes just to see where everyone was at in regards to probability. And then we reviewed some. I didn't really review those problems, but I reintroduced you to the concepts of probability, and now I would like to continue with that. So, if you would, without wasting much more time, because I would like to, but whatever, I'm going to need those notebooks out and open. Something I would suggest, along with having your notebooks out, would also be having those calculators ready to go, only because there are going to be certain problems that I would suggest that you practice calculating. You need to know how to type these things in correctly into the calculator. And a lot of the time, it's very straightforward, very simple. But if you haven't had the very basic practice with it, then it's going to be one of those things where in the moment when you actually have to do it yourself, you're going to be like, oh, crap, where did I go wrong kind of situation. But regardless, today is December 2nd. We made it. Something I just thought about. You're technically done with over 30% of the school year. 30%. It's really messed up. Anyway, we're going to call this probability continued. Probability continued. Because that's exactly what this is. Sorry. My wife sends me conversations between her and my kids. And apparently she was waking up my son this morning, and my 2-year-old daughter walks into the room with a teapot, a spoon, and just a shirt on. Nothing else, just a shirt on. And she proclaims that, with the teapot and the spoon, she proclaims that she's stirring. And so my wife asks her, "Where are your pants?" And she pauses for a moment and then just yells at her, "I'm stirring!" Oh, I just thought that was hilarious. But anyway, enough about my kids. Let's get into this. Now, last class, I left off talking about a certain formula that I'm going to write again. I'm going to write the formula again just for the sake of argument. And then I'm going to do an additional problem, one that we did not do, the last time. But you'll see. The formula was the probability of A or B. Now, again, we wrote this down last time. I'm going to write it down again just for the sake of consistency. just so I have a reference to it. But if you have the probability of A or B, then typically you can calculate said probability in the following way. You can calculate it by finding the probability of A, adding, I want to emphasize adding the probability of B, and then subtracting the probability of A and B. So for example, and I'm going to go back to my weird looking die thing. Oh, hold on. Cool. I'm going to go back to my weird looking die thing right here, which again, I can't find the regular die, but this is the die that I have right now. Cool. But if I were to roll this die and I wanted to find the probability of rolling, let me think of a good example. Okay. Yeah, there we go. Cool. If I wanted to find the probability of rolling a die and getting an even number, or let's just say a perfect square. Let's call it a positive perfect square. A positive perfect square. Just to be very detailed about that, I know. Positive perfect square. The reason why I say that is because I don't want to mess with the number 0. So 0 is neither positive nor negative, but whatever. I digress. So in terms of an even number, if you looked over this cube, this particular cube, which doesn't have a 6, 0 is positive nor negative. We're not going to count it as, actually, no, technically we could count that as let's count that as even technically. Yeah. So we could say 0, 2, and 4. 0, 2, and 4. 0, 2, and 4, meaning there are 3 out of 6 that are even. And then I would add positive perfect squares, which if you go throughout this cube, positive perfect squares, there's only one, and that's a 4. That is the only one that is a positive perfect square. So I would add 1 out of 6. So the 3 would be for getting the 0, the 2, or the 4. That would be the even. And then getting a positive perfect square is getting that 4 again, which, oh no, I'm counting it twice. But then you would subtract what they have in common. You would subtract the probability of getting both, which in this case would be, again, a 1 out of 6. Seems kind of weird to do that, but this is what the formula does. It ends up being 3 out of 6, which reduces to 1/2, which reduces to 0.5. But this formula can come in very handy, especially when you're dealing with OR type problems. Very strange, very strange. Now, there is a very specific rule that you can do for AND problems. There's a very specific rule that you can get for AND problems, so I'm going to get into in a moment. I will get into it in a moment, but I wanted to give you a brief definition real quick. There is this concept using this formula known as something being mutually exclusive. Mutually exclusive. Here's a definition for you that I would like you to write down. Events A and B are, quote, mutually exclusive, end quote, if the probability of A and B is equal to 0. Now, what that means, if there is no overlap between the two of them, if the probability of both happening cannot happen at the same time, then you would say that the two events are mutually exclusive. For example, and I'll go back to an example that we did 2 days ago. The example that we did 2 days ago that I'm going to write down more detail for it, was a deck of cards and getting the probability of a king or a 10. Now, we know the probability of getting a king is 4 out of 52, and we know the probability of getting a 10 is 4 out of 52. But ask yourself the question, what is the probability of pulling one card from a deck of cards and it being both a king and a 10? It's not possible. It's not possible. If you were to create a Venn diagram for kings versus tens, if you were to create a Venn diagram for kings versus tens, well, it would be the king of hearts, the king of spades, the king of clubs, the king of diamonds. I'll zoom in on that. It would be the 10 of hearts, the 10 of spades, the 10 of clubs, and the 10 of diamonds. But there would be nothing in the middle. Nothing. These two events, by definition, are mutually exclusive. Where you would go 4 out of 52 plus 4 out of 52 minus the probability of kings and tens, which, per our definition earlier, is 0. They are mutually exclusive events. So I would say getting a king and a 10. I can't see it. I'm going to zoom out. Woo! There we go. Getting a king and a 10 on one draw is impossible. They are mutually exclusive events. AKA, and I'm going to read this again. But I'm going to give you the AKA one more time. AKA is also known as, just for the record, getting a king and a 10 on one draw is impossible. They are mutually exclusive events, AKA disjoint. When you have two events that are mutually exclusive, you would also refer to them as, that is also known as, AKA, being disjoint, meaning that there's no overlap between them. They are disjointed from one another. We could basically separate these two circles in the Venn diagram and nothing would change. It's kind of nice. Whenever you hear the phrase mutually exclusive events, that's what I want you to think of. The fact that they cannot happen at the same time. They can't. Impossible. Anyway. If there is overlap between them, if there is something in the middle, then you would just simply say that they are not mutually exclusive. Now, that word or right there, king or 10, whenever you hear that word or in the realm of probability, I want you to be thinking of the concepts of adding and subtracting. Because if you hear that word or, I want you to be thinking of that formula, the probability of A plus the probability of B minus the probability of A and B. That's what I want you to be thinking about. But if you're thinking about the word and as a problem unto itself, which obviously for this problem, there's nothing you could do here. You could easily just figure out the probability of both just by thinking about it. But if you ever had to do a problem where the word and was coming into play, I want you to be thinking about multiplication. I want you to be thinking about multiplication. Now, there actually are technically two different ways you could do the multiplication formula, because there actually is a brand new formula for this. And I'm going to put that on the next page, actually, just so I have a little bit more room to kind of write that thing out. But we'll get that thing done. Yeah, I'll put that on the next page here. So I'm going to split my page just a little bit. And on the left side, I'm going to write the probability of A and B is equal to the probability of A times the probability of B. Again, when you see that word and, I want you to be thinking multiplication. But there is a second formula. The probability of A and B is equal to the probability of A times the probability of this. Now I'm going to pause here for just a moment. And stand up to emphasize some stuff. I'm going to zoom in up here to make that a little bit more palatable, viewable, and things of that nature. There's more, obviously, that I have to add to this thing, but I want to get up and actually explain what in the heck is going on with this thing. Bring this up just a little tad. There we go. Good. So there's no typo up here. Keep that in mind. There's no typo. The probability of A and B, the probability of A and B. They're both the same concept, but they're slightly different formulas. In this situation, you would just multiply the two probabilities together. Oh, happy day. Over here, you would still multiply, except you got this little thing going on here. Now, what the heck is that? Now, the way that is written, and I'm going to write that a little bit larger so you can see exactly what I'm referring to, because I need you to be able to recognize what that is actually saying. This is saying the probability of B given A. Literally, that is a vertical line. It is not a division sign. That is a vertical line. And you would read that vertical line as the word given. It is the probability of B given A. Now, what in the heck does that mean? We'll talk about that in a moment, but I just want you to be able to recognize how to read that properly. B given A. Now, what it actually means, well, it depends on what the two events are. In the past, you may have done problems with, let's say, like a deck of cards, and what's the probability of picking out this card, and then you go to pick a second card. But then that second event depends on whether or not you put that first card back. In the past, maybe like in middle school or late elementary school, you may have used the phrase with replacement or without replacement or some junk like that. Were the probabilities reset? If I were to have a deck of cards, actually, I don't know where they went, actually, tell you the truth. Again, I did have a bag of marbles back in the day. They have to be somewhere. Regardless. Oh, is that them? Oh, I may have found them. Give me 1 sec. Hold on. Aha! I did not find my bag of marbles again. I did not. But I did find my decks of cards. That was great. So, again, the bag of marbles is somewhere in this room. But I have misplaced them. I've misplaced my bag of marbles. One might say that I've lost them. Anyway, back to this. So I have a deck of cards here. Very basic deck of cards that you got going on here. You can see, boom, there's the deck of cards right there. There are 52 cards in this thing. There are 52 cards. Great, fantastic. And if I were to randomize them, obviously, with the shuffle, you can't really see this. I'm going to do it on the table, but it makes that cool noise, at the very least when you shuffle them, But if they're randomized, and then if I were to pull one card out, shabam, Ace of spades. Was it? Yeah, the ace of spades. There is a 1 out of 52 chance that I would have gotten the ace of spades. There is a 4 out of 52 chance that I would have gotten an ace. There is a 13 out of 52 chance that I would have gotten a spade. But now I'm going to draw a second card. Now, am I going to put it back? Am I not going to put it back? If I put it back and then reshuffle, I'm dealing with this. If I put the card back and reshuffle, I'm dealing with this, where all of the probabilities are now reset. But if I don't put it back, now all of a sudden I'm dealing with this, where now the second event, B, depends on what happened with A. B given A. It is event B given that event A has already happened. Let me write this out a little bit. Let's see. Now, this probability right here would happen if events A and B are independent. That exact concept would be used if events A and B were independent. And I'll show you various examples of that. But then you would use this formula if events A and B are dependent. If I could spell dependent, dependent. If the events are dependent on each other, if the probability of one of the events changes dependent upon what the first event did. So the example that I can do, again, I'm going to draw the ace of spades, or, whatever. We'll figure that out in a moment. So let's just say I wanted to find the probability of, let's just say getting a spade and a heart. Okay. The probability of getting a spade and then a heart. Now, I'm going to be very clear about this. We're going to say with replacement. With replacement. Meaning I put the card back randomly. So 52 cards are in the deck. The probability of selecting a spade is 13 out of 52. Now, I say with replacement, meaning there's the deck of cards right there. There's the ace of spades. I put it back in, and then I randomize it again by doing the whole shuffle deal. Man, these decks are stiff. That's weird. And now I'm trying to find the probability of selecting a heart because I put that first card back. So the probability of selecting a heart, bam, multiply 13 out of 52. Now, again, if I were to do that on my calculator, which again, you should have the practice with doing something like this, I would type it in like this. Parentheses, 13 divided by 52, parentheses, you can put a multiplication if you want, 13 divided by 52. You could put a multiplication symbol between them, although the calculator assumes it's there. I would just suggest definitely using parentheses, especially moving forward with whatever the heck it is that we have to do. A spade and then a heart, the probability is 0.0625 or 6.25%. Wonderful. But now I do this. Dependent events. The probability of getting a spade and a heart without replacement. Meaning, I am not putting, why did I put that parenthesis there? I am not putting the card back. I'm not putting it back. And if I don't put it back, I don't know where my ace of spades went. There it is. Ah, there's the ace of spades. So I pulled the ace of spades. I'm going to leave it up top. The deck is still technically randomized. And now I have to pick another card. Hold on. I want it to be a heart just for the sake of argument. There we go. So now I got to pick a second card. Now, getting that ace the first time was 13 out of 52. But now that the ace is no longer there, what's the probability of selecting a heart? Well, there's still 13 hearts, but now there's only 51 cards to choose from. That changes the probability. It changes things. It changes the way that this thing is calculated. Now, it may not change the number all too much, but I just want you to be aware of something like that. Ah, weird. So let's actually do that. 51. There it is. Now, it changed it ever so slightly. It got you a 0.0637 approximately. A 0.0637. That's a 3. That's weird. But now look at the change in probability. What is the probability of getting a spade and a heart? Well, if you don't replace the card, it's a slightly better chance. Slightly. This is how people are able to cheat at certain basic games of gambling. If you are playing blackjack, for example, then you may be able to mentally keep track of which cards have been played. Sorry, I just saw your comment. That was funny. But yeah, if you're playing blackjack, you can keep track of which cards have been played. Now, typically, it's a lot easier if you're playing at a table with a lot of people, where you just casually glance at what cards you've seen. It's a very basic counting technique where you count high cards as like you count high cards as a negative number, you count low cards as a positive number, you count cards in the middle as 0, and then you keep track. And then if the count in your head reaches a certain value, then you know that there are going to be some high cards coming out, like 10s and kings and aces and things of that nature. So then you tend to bet a little bit higher. Casinos actually have a rule that they play with multiple decks of cards so that it's more difficult to keep track of counts. And then eventually they actually switch out the decks every now and then, or use a brand new deck at the beginning of every hand or some junk like that. They have techniques to kind of parlay that. There was a movie made about a similar concept a few years ago called 21. I know you guys may or may not have heard of it, but it was about a bunch of MIT students traveling to Vegas on the weekends and scoring, a lot of money using their mathematical techniques in order to cheat at gambling. Technically, it wasn't cheating; it was just gaming the system. But I digress. Oh, crazy stuff! Get rid of that. There we go. So let me give you another just kind of basic example. If I had a coin, flipping a coin is another basic probability example. And I do have a penny right there. There's my penny. Let's zoom in on Lincoln. See how much detail we can get on Lincoln. Hold on, it'll focus. That's not bad. I wish I had a better camera than this. I need to get a better camera. Let's zoom in on the date right there. See how good I can get. Oh, that's too far. Yeah, that wasn't bad. See, I need something like this at home. I'm a coin collector, but the quality on that is not that very good. But anyway, you have a coin. It's a fair coin. Now, it's fair to say that the coin has no memory as to what happened before. So I'm looking for the probability of flipping the coin and, let's say, getting heads, then tails, then tails. See, by definition, I don't have to do with or without replacement, because when you flip a fair coin, the coin has no memory as to what happened beforehand. So by definition of how the coin works, each event is independent of each other. By how the coin works, I can say that each event is independent of each other. So it doesn't really matter. I could say, okay, well, then it would be 1/2 to get the heads. Now, mind you, I didn't write the word and, but you have to assume that this is an and problem because it's heads and then tails and then tails again. So I would multiply, getting a tails is 1/2, and then I would multiply, getting a tails is 1/2. It seems silly to do it like that, but that is exactly what is happening with this problem and this process, where I would take those three and I'd multiply them together, and it would actually 2, 4, 8, yeah, it would get you a 1 out of 8, or the exact decimal. If I can get the exact decimal here. Yep, I should have guessed that. 0.125. 0.125. A coin has no memory as to what happened beforehand. So by definition, it's going to be independent events. Just keep that in mind. It's very strange. It's very strange. In fact, think about the following concept. I'm going to give you an example problem just to kind of think about this, because there's a certain definition that I'm coming up to in a moment. A coin is flipped 100 times. A coin is flipped 100 times. The first 99 results were heads. The first 99 results were heads. What is the probability of getting tails on the next flip? Now, don't answer right now. I really just want you to think about this. Think about this concept. This concept is incredibly important in regards to probability. Now, one could argue that this coin is flawed. It's flawed because who in the right mind would get 99 heads in a row? That's weird. But it is still possible. It may not be probable, but it is possible to get 99 heads in a row, which begs the question, what is the probability that you're going to get tails on the next flip? Now, again, I just really want you to think about this. Literally, imagine you sitting in a room. Maybe you're flipping a coin. You would rather be flipping the coin than paying attention to whatever the heck it is that you are doing in class. So you flip that coin, and 99 times in a row, you get heads. And then someone's like, oh man, what's going to happen on the next flip? And then you think about it. Well, I'm probably due for a tails. I mean, tails has to happen. Maybe there's a better chance, but there's not. There's no better chance for getting a tails on the next flip. There's not. It's still a 50-50 50-50 chance. Now, some people would argue this concept known as what they call the law of averages. Well, law of averages, you got to get tails. Not necessarily. Not necessarily. On the very next flip, what is the probability of getting a tails? It's still 50%. It's still 50%. Assuming that it's a fair coin, it's still 50%. I think of like a baseball player. If you have a baseball player who maybe like career, they're like a really good hitter. Let's say during their career, they're a really good hitter. I'm not going to get into the numbers for baseball averages and things of that nature. But let's say this really good hitter is having a very bad week. Now, normally, let's say that this hitter gets a hit 30% of the time. Let's just say 30% of the time. Cool. 30% of the time, this guy gets a hit. I don't know, it's Derek Jeter. Cool. Derek Jeter is probably a career 300 hitter anyway, but still, 30% of the time he gets a hit. But then there's a week that goes by where he has a slump and he doesn't do as well and he strikes out more. And let's say for the past 3 games, let's just say he has no hits. If people were writing news articles about Derek Jeter, 3 games, he's had no hits. Man, he's due. What does that mean? He's due. Law of averages. He's got to get a hit sooner or later. He's got to break out of the slump. No, he doesn't. If he gets a hit 30% of the time during his career, then the very next time he comes up to bat, he still has a 30% chance of getting a hit. He doesn't have a better chance because he hasn't been doing as well. There is no such thing as the law of averages. There's no such thing as the law of averages. Just what happens next. What is going to happen next? Certain probabilities don't necessarily change, especially with the coin. Let me answer that question, by the way. What is the probability of getting tails on the next flip? 1 in 2. 50%. That's what it is. Now, you may be able to measure something if you're dealing with, let's say, like a deck of cards. Now, a deck of cards only has 52 cards. If you have, pulled 48 of them. Hold on, let me do an example here. Hold on. Now, this is a different scenario. This is a different scenario because of the dependence of things happening. There we go. If check this out, I'm going to do this example. I'm going to zoom out a little. You'll see this. 52 cards in a deck. Now, let's say I'm not going to put them back. Let's say I don't put them back. And I were to be like, okay, I'm going to draw these cards one at a time. One at a time, I'm going to draw these cards. And let's say, man, I've drawn 48 cards. I'm going to speed this up a little. Let's say I've drawn 48 cards. What is the probability? Man, I haven't seen any aces. I haven't seen any aces whatsoever. This is card number 48 right here. What's the probability that the next card's going to be an ace? Well, now this is a different scenario because this is not about the law of averages. These are dependent events. This is a finite number of cards that you got going on here. Let me give you a couple definitions. So, if events are independent, and I want to emphasize independent, meaning one does not depend on the other. This is putting the card back into the deck. This is resetting that coin. If events are independent, there is no such thing as the law of averages. There's no such thing as the law of averages. Now, one might argue in terms of Derek Jeter and baseball, you might be like, well, if he hasn't been doing very well, If he hasn't been doing very well, maybe on the very next at bat, he's going to try a little bit harder to get a hit. Maybe. You don't know what's going through his mind. In baseball, we assume that each at bat is independent of the next. Now, obviously, the human factor has to be taken into account. But if you're taking the entire man's 20-something year career, you have to assume that if you pick an at bat at random, there's got to be a 30% chance that the guy gets a hit. If you're picking an at bat at random, if the events are independent of each other, like flipping a coin 100 times, there's no such thing as the law of averages. Probabilities remain the same. Now, I want to emphasize this is if they are independent of each other. They have to be independent of each other. If the events are dependent on each other, then all bets are off. Ugh. But there is such a thing as the law of large numbers. And I'll explain what that is in a moment. With an anecdote. I love anecdotes. But there is such a thing as the law of large numbers. There was a man who was locked in a prison cell in England, maybe somewhere in Europe, but during the 1700s, maybe 1600s, whatever, don't care. And this man was locked in this room. It was a small stone tower room with a small slit at the top to let air in that he couldn't reach, and a metal door with a slit where they could put food in, and beneath him a drainage system for use your imagination. And this man was put in jail for the rest of his life. The only thing that he had with him was a coin. Now, I can flip a coin 5 times, and I can get 5 tails. 100% tails. Well, that doesn't make any sense. No. That's possible. That is possible. Not probable, but possible. But then we come to something called the law of large numbers. This man, for the 30 years of his life that he was locked in prison, had a coin with him. In order to keep himself sane, he would flip the coin, record the result on the wall, and then move on. Now you're like, how did he record the result? He recorded the result with using the coin to carve it into the stone. Then, after he died, they found out that he died, obviously, because he wasn't returning the food trays. They would give him a food tray with food on or whatever, and he'd eat it, and he'd return the food tray. Cool. And then one day he didn't return the food tray. And they're like, oh, he died. Cool. So they went in to take his body out. No one had been in that cell for 30 years, except for this man and his coin. And when they went in to take his body out, the walls were covered in tally marks. Every spare inch was covered in tally marks. This man had been tallying the results of heads versus tails on the flip of a coin for 30 years. Which begs the question, well, what happened over the course of 30 years? Over the course of 30 years, what happened was the law of large numbers. Now, in the beginning, you may, now here's 100, let's say 100% tails, and let's say 0% tails. We would assume that it should be 50-50. In the beginning, let's just say 50% is right there. There we go. in the beginning, he may have been like 60-40 tails, and then it may have dropped to like 45% tails, and then it may have gone up and then down and then up and then down and then up and then down and then eventually it levels out. The general concept is this. As the number of trials that you perform grow larger and larger and larger, then the experimental probability, the experiment of actually flipping the coin, the experimental probability approaches what we call theoretical probability. Let me give you those definitions. This is what we're going to wrap up with today, by the way. This is what we're going to wrap up with today, but I want to make sure I get these definitions down to you. So first, let me tell you about theoretical and experimental. And then I'll give you the definition of the law of large numbers. Theoretical probability basically is what should happen. Theoretical probability is what should happen. I flip a coin, I expect it to be a 50-50 coin. Experimental probability is what did happen. Theoretical is, oh, well, this is what should happen before I actually do it. But then experimental probability is you actually performing the experiment or whatever it is that you're doing. And then it's like, oh, I got 60-40. Okay, no harm in that. You got 60-40 tails. Cool. What should have happened was 50-50, but what did happen was 60-40, and that's nothing out of the ordinary. That's fine. Experimentally, you can flip that coin 100 times and get 100 tails. Yay, you did it. But the law of large numbers basically states, as the number of trials increases, as the number of trials increases, experimental probability, which I am abbreviating, approaches theoretical probability. So if you had a fair coin, is it possible that you would get something ridiculous like 1,000 tails in a row? Yes, it is possible. It is entirely possible for you to get 1,000 tails in a row. But as the number of trials increases, as it gets larger and larger and larger and larger, the number of trials, then your experimental probability should be approaching that theoretical, in this case of the coin, 50-50. If you're rolling a die, and it's like, I want to roll a 5. Well, how often should a 5 show up? A 5 should show up. Let me show you the 5 here. The 5 should show up about 16.7% of the time. 1 in 6. And if you've rolled that die like 100 times and you've never gotten a 5, you'd be like, oh, maybe there's something wrong with the die. But if it is a fair die, then eventually, over the course of the long run, the law of large numbers, many trials, eventually that experimental probability will approach 16.7% for that 5. That's what this thing is doing. It's so great. Now, I know today was a bit more note heavy. I kind of needed it to be because I needed to get that information out to you. The next time I see you, which will be on Friday, I am going to be going over various practice problems with you. I am going to be throwing a worksheet at you. A worksheet, a practice worksheet at you on Google Classroom. We'll get that thing done. It will be fantastic. But it's meant to be practice. It's meant to be like a homework practice kind of thing, So it's meant to see like, okay, am I understanding this more? Am I doing this better? Am I actually calculating out these numbers? I want you to be able to use what we did last class and this class to get this thing done. It's going to be phenomenal. I'm going to assign it sometime before I leave here today because I can't assign it exactly right now. I got things to do. But anyway, I'm having too much fun pretending I'm hosting a show, but in reality, there's like no one here. Makes me sad. Anyway, you guys have a wonderful morning. It's still morning. I'm going to go make a cup of coffee, but I'm going to sign off. See you guys. Goodbye, 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 goodbye. Take your stuff from under the desks. Don't leave them here. Whatever. Anyway, see you.